So let's rewrite what we have. We know that an individual piece of the line emits an electric field that's equal to K. Now here we have dq. We're going to substitute in lambda dx for dq. We have 1 over r squared, so we're going to have x squared plus y squared down here. Again, we've got our geometry from our coordinate system to put in here. And then we've got r hat. That's a bit messy looking. That's going to be xi hat plus yj hat all over the square root of x squared plus y squared. And now we want to get the total electric field. E vector, we're going to integrate over the dx from negative infinity to positive infinity. That's the beginning and end point of the line. And we're going to integrate this thing. K, which is just a constant, lambda, which is a constant in this particular problem, dx. Now I'm going to simplify the denominator here. I'm going to combine x squared and y squared and the square root of x squared and y squared. And if you're not sure how this works, please go and study your square roots and remember what that means. X squared plus y squared all square rooted is the same as x squared plus y squared all raised to the 1/2 power. And so when I multiply these two denominators, I get 3/2 down here. If that's not familiar, go practice that. That'll be very helpful. And then finally we have xi hat plus yj hat. Well, we actually have two integrals to do here. They're summed together. One is over the x component, one is over the y component of this unit vector. So we have ex. We can break this into pieces. That's the integral from negative infinity to infinity of k lambda dx all over x squared plus y squared to the 3/2 x I hat. And we also have ey, which is equal to the integral from negative infinity to infinity of lambda dx all over x squared plus y squared to the 3/2 y j hat. Okay, a couple of things here. At this point, when you've got an integral like this, I don't expect you to just know this off the top of your head. This is the 21st century. There are computers, there are books, you should use them. Okay? And on an exam, I would be providing you with a range of possible outcomes of a given integral, and you could choose from choose the one that's appropriate to the problem you're solving. So let's be realistic. You're going to look this up in a book. And what you're going to find out is that this integral for ex is equal to 0. That's the way I write 0, just in case anybody's wondering. Okay, that's very useful, because what we find out is that all the little fields along the x direction from the left side of the line and from the right side of the line all cancel out in the end. And that means that the total electric field does not have a component along the line itself. That leaves us just with ey. And what we find out there is that ey is equal to 2k lambda all over y, and that's in the j hat direction. In fact, because the x component of the total electric field is 0, this is also equal to E vector, because E vector is entirely pointing in the y direction, and it has a strength that falls off linearly with your distance from the line. If we go back here, this distance here, this is y. That's your distance from the line, and that's the only thing that matters as regards the strength of the electric field from a very long, very thin line of charge. This is actually quite astounding. A point charge has a field that falls off as 1 over the distance squared, but in a line, all of the point charges' electric fields are working together in concert to create a stronger field than is possible from any one of the charges. And so rather than falling off quickly as 1 over r squared, it falls off very slowly as 1 over r. Remember, the dipole field fell off as 1 over the distance cubed. That one falls off even faster. So this is somewhere in the middle, and this is a very interesting field. If I were to draw this field, which I can do on this piece of scratch paper here, let's imagine this is my line, and it's infinite. I haven't drawn it infinite, but I can pretend that's infinite. The electric field lines radiate out from the wire and their strength falls off linearly. So this is what the electric field of a line, an infinitely long, uniformly distributed line of charge, looks like. And you can imagine this field repeating at every point along the line. And so you have this electric field that stretches out and falls off linearly from the wire. And in fact, if you measure the electric field from something like a copper wire, where the length is much longer than the thickness, you will find that this is in fact true, that the strength of the electric field does. So this is a very good archetype for a wire. Now, a little note. We're going to skip chapter 21. Chapter 21 covers something called Gauss's law, which I will mention briefly in the future. Gauss's law gives you the ability to much more easily calculate the electric fields from much more complex objects like planes, spheres, and cylinders. Instead of making you go through the rigor of doing Gauss's law, we're going to move on to electric potential and voltage and electric circuits. Instead, what I'm going to do is I'm going to equip you with the electric fields from some of these more complicated things, planes and cylinders and spheres. One thing you find out when you're working with Gauss's law is that you see the following quantity appearing quite a bit. You see 1 over 4 pi k, or more specifically, just 4 pi k, appearing all the time. And so what we do is we absorb this product of three constants, 4 and pi and k, into a new constant called epsilon naught. Epsilon naught is equal to 1 over 4 pi k. That's the definition of epsilon naught. And it does have a value. Its value is 8.85 times 10 to the minus 12, and you could of course calculate this yourself just by taking 1 over 4 pi k. And as you can imagine, because it's 1 over k, the units are slightly different than k. They're coulombs squared over Newton meters squared. That's epsilon naught. That's what it's equal to. 8.85 times 10 to the minus 12 coulombs squared over Newton meters squared. The nice thing about epsilon naught is it helps get rid of some of these 4 pi's that wind up floating around in calculations of much more complicated shapes. So let's talk about a few of those right now. Let's imagine we have a cylinder that is charged. It's a thin-walled cylinder. It's hollow. Okay, so this is now essentially a line, but with a non-negligible thickness. And it's hollow. And the walls of the cylinder are charged. And so you can, again, go through the exercise. This is very hard to calculate using Coulomb's law. It's a lot easier using Gauss's law. And I'm just going to give you the answer. So the answer is that outside of this cylinder, if you're anywhere out here, let's say a point P outside the cylinder, the electric field is given as lambda, the linear charge density. Okay, so we have some linear charge density, lambda equals dq over dx, where dx is along the cylinder's length. So we have a linear charge density lambda divided by 2 pi epsilon naught r, your distance from the center of the cylinder, and that's in the r hat direction. That's in the radial direction pointing out from the center of the cylinder. Nifty enough, inside the cylinder, the electric field is entirely zero. All of the electric fields of all the charges inside the cylinder cancel each other out. That's very useful. If you're ever inside of a cylinder full of charge, you have nothing to fear from electric fields. In fact, this will be a very useful thing when we talk about how you're protected from lightning. Now, what about a plane? A plane is a two-dimensional surface. It's flat, and it has an area charge density, sigma, which is the total charge over the area A. And again, you could consider little pieces of the plane, dq, and little bits of area, dA, that they occupy. The bottom line is that the electric field from a plane of charge is equal to this area charge density divided by 2 times epsilon naught, and it points vertically out from the plane above and below the plane. So it's about as close as you can get to something that generates a perfectly uniform electric field whose strength does not decrease with distance. Again, this is for an infinite plane. There's no such thing as an infinite plane in the real world, but there are very large sheets of charge compared to the sizes of the things in question. For instance, when you are doing electrophoresis to run DNA through an agarose gel, which you may have done in a lab before, the electrodes at either end of the agarose gel serve as infinite planes of charge compared to the size of DNA molecules, and the electric fields that those electrodes create are very uniform inside the agarose, and that allows the DNA to be accelerated through the agarose gel. Different sized genes move at different rates. So this is already something that's applicable in a biological context or in a forensics context. Finally, we have the sphere. Sphere is just a ball, and you usually characterize it as having an outer radius, capital R, so a sphere of radius, capital R, and then you're usually interested in measuring the electric field at some point P, a distance little r vector away from the center of the sphere. And much like the cylinder, we can start by considering what the electric field looks like outside the sphere. So outside the sphere, what you find is that the electric field is equal to the total charge on the sphere, Q, we'll say the sphere has a total charge Q, divided by 4 pi epsilon naught r squared, and that's in the r hat direction. And you'll notice that this actually looks just like Coulomb's law. If I substitute epsilon naught with 1 over 4 pi k, we see that we actually recapture Coulomb's law. So in fact, when you're outside of a sphere, it behaves just like a point charge. And this is why we can get away with treating tiny little balls of stuff like they're point charges, because they look like a point charge outside of the sphere. Now, if the sphere is solid, that is, if the charge goes all the way down to the center, like a tiny little ball of candy, then the electric field inside will not be zero, but it will decrease with the distance inside of the sphere. And in fact, what it looks like is k, q, r, your distance from the center of the sphere, over big R, the fixed radius of the sphere cubed. If it's hollow, if you just have a thin shell of charge that defines the boundary of the sphere and then nothing inside the sphere, just like the cylinder, all the electric fields cancel out and the electric field inside is zero. And again, that's for a hollow cylinder only. For a solid cylinder, something that has matter or material charge that extends all the way from the shell into the center of the sphere, and if it's uniformly distributed, then you wind up with this situation where the electric field falls off as k, capital Q, little r, your distance from the center of the sphere, over big R cubed. All right, well, let's think about what the lesson is here. The lesson is that calculus lets you connect point charges to large distributions. Coulomb's law works just as well in this environment as it does on a solo charge or two charges. And archetypal shapes, like an infinite line of very thin extent, they actually have interesting electric fields, and you can immediately find things in the real world, like cables, which can be modeled using an infinite line of charge. I want to thank you for listening to this mini lecture, and I'll see you in class.